Hello, welcome back. In the last video we talked about this DeepSeek V4 pull request into vLLM. In this video we're going to look at the fusions. So in particular, there's all of these custom kernels. What are they doing? So before we get into this, let's talk about GPUs. So every time you launch some computation via a torch op, you're doing a few things. So one is you're going to copy your tensors from GPU high bandwidth memory, HBM, to the compute units. You're then going to do your compute and then you're going to copy it back. So if you do this very naively, what you're going to end up doing is a lot of data movement. You're going to copy, do one operation, copy back, etc. So the name of the game in deep learning is to do fusions, where you have a single kernel that does a lot of stuff and then you copy back. So for example, if we look at DeepSeek V4 and we look at the gate before the MOE, we can actually fuse all of this code into a single kernel. And indeed, you can see here that basically the code I highlighted previously becomes this fused Hopk bias. Similarly, for hyperconnections, we can do fusion. So these three fuse into this. There's like 10 plus things fuse into this. Similarly, we can take these two nested loops in the hyperconnections posts and fuse into a single kernel. We can fuse the head projection after all of our transformer layers into a single kernel. We can also, when we're doing the QKV, not only can we fuse it together, we can also do the page, the KV cache writing as part of our kernel as well. For the output projection after attention, we can also do this in one pass, which includes the quantization. Similarly, for activation, we can basically fuse all of these ops into a single operation. This one's pretty interesting. So, mixture of experts, we're doing a series of map moles for each expert, but we can actually do what's called a grouped gem and do all the matrix multiplications all in one go in one kernel. For the index or scoring, we can also fuse it. And these last two ones are interesting because they utilize the KV cache as input. And if you naively do this, you end up having to copy out of the KV cache and having these intermediate tensors. But basically by having this fused kernel, we can just read directly from the KV cache. And that ends up being a lot more efficient. And then lastly, for attention, we use Flash MLA. And it's Flash MLA with KV cache awareness. And so we can basically read the caches in place without having to do these intermediate tensors. So hopefully this was useful. This kind of gives an overview of the high-level fusions that's happening for DeepSeek V4 and vLLM. In future videos, we're actually going to look at some of the CUDA kernels and see how we actually write these kernels efficiently. So yeah, see you in the next one.